like to share some of my opinions about cause discovery. So therefore, I could have definitely have some bias based on my literature studies and my works. So if you know more, if I was wrong somewhere, please just correct me. And then, so today's talk I will just, because I assume like today's audience, I assume you don't have any knowledge about cause discovery, so this will be a very brief introduction in the basic level. And then I will mention some connection about the cause discovery and machine learning studies. Yeah, let me start. So maybe I could give you some causality examples. Actually, causality is not something we are not familiar with, and it actually happens in our daily life. We could see it in the report, in the papers, in the newspapers, and you can see like explained by or something leads to something, or you could also see some figure like these, like the chocolate consumption and Nobel Prize, number of Nobel Prize. So you could say, okay, so what is causality and why it is so important? And now, in order to answer the question, I would like to share a very concrete example because the previous one are too blur. Yeah. So the example is made up by me, so nothing is real here. It's just for demonstration. Well, let's imagine that we are given a causal graph, or maybe I could highlight this. Laser point, good. So actually, this example is based on the pandemic experience, maybe something about COVID-19. And then, so firstly, we are given a causal graph. We want to show how can we use causal graph or causality for our daily research or applications. So now we are given a causal graph. And this causal graph actually tells us that, okay, we are interested in the status of our patients, and we have some special medicine. And we have another variable which tells us like whether a patient has a fever or not. Then this causal graph tells us, okay, there is a causal relationship between the medicine and the status of the patient. Meanwhile, the fever has an effect, has an influence on the medicine, which means whether we give a medicine to the patient depends on whether the patient has a fever or not. And this actually direction or arrow tells us that whether this patient has a fever have an influence on the states of the patient. So if this patient has a fever, they will feel bad or good. And now we are actually interested in one thing. We want to know whether this submedicine, a specific medicine, is effective or not. And what can we do? And then, for example, we could do randomized control trials. We could also think maybe we want to use some data-driven method. So we collect data, and then we have some data. We just randomly collect data. We come to the patient. We ask them whether you have a fever or not, and then we ask, okay, have you ever taken any medicine? How do you feel after you took the medicine? And then we have such data set. And one means, okay, this is a good. It's like I feel better. And this one here means, okay, I took the medicine. And this one here means that, yeah, I do have a fever. Yeah, let's move on. So in order to answer the question, we could use randomized control trials. Of course, this is a very this is a simplified randomized control trials. This is not something in practice. So for example, now we have a group of patients. We split them into two groups, randomly split them into two groups. And then we give them medicine. We give the medicine to the first group, And then we give nothing effective in the capsule to the second group. And then we see after they take the medicine, whether they become better or not. And then we see the recovery rates, and then we make some conclusion based on that. And you may have already seen there are some issue about that, but we can come back to that later. Because, for example, the ethical issues, whether we are allowed to do that or really, or is it very expensive? But let's just put this method here and think about something else. Can we do something else? Since we have already got a data, can we do something with the data? Yes, of course. What can we do? So, for example, we can compute the conditional probability distributions of all the variables. For example, we compute the probability of the status of patient conditioning on the medicine. So like they took the medicine here. This capsule equals to 1 means, okay, we only consider a group of patients who took the medicine. And here means who have never taken any medicine. And we compute, okay, the frequency of the good states. And then we observe, okay, in the data set I collected, we have this probability. I have, again, the same probability. Then we will, okay, what does it mean? Does it mean this medicine is effective, or does it mean the medicine is not effective? So we don't know because they're the same. So maybe we could conclude, okay, it doesn't help. At least it didn't make things become worse. Then we compute something else. Like, okay, so now we only have a look at the group of people who have a fever. Then we compute exactly the same thing here. We get a number. Then we get another number. Then this actually gives us another conclusion that, okay, if we consider to use the second row of probabilities, actually the medicine is helpful. Well, which one should I take? So actually there are some conflicts with each other, which depends on which conditional probability you use. However, I want to say that the misleading is not actually, it doesn't mean we cannot use the observational data to make a conclusion, but it means that we need a more careful way to compute the probabilities. So for example, in causal inference, there's a concept of interventional distribution. It is actually doing something similar to the randomized control trials. So in the randomized control trials, there is this kind of randomly give patients medicines. It is actually trying to break the arrow from the fever state to the medicine. So whether a patient take a medicine or not is not depending on the fever state anymore. Then we were wondering, okay, now what is the effect of the medicine, right? So we control a variable, we break this misleading relationship, then we see what happens else. And then in the causal inference, it is actually computing the interventional distribution to see to check the effectiveness of the medicine. So for example, here, this is the interventional distribution and probability. And then instead of computing this conditional probability, we condition this interventional probability. And the only difference here, you may have already observed that, is here it uses marginal distribution instead of the conditional distribution. Because this graph is actually we are using, but we don't have the data of it. So the idea is that we want to use the data from one causal graph to compute some probabilities and use that one to represent the causal graph we want to use, because we don't have data of this. So here's the basic idea of interventional distribution. And then we can make some conclusion about, okay, whether it is effective or not effective, something like that. Here, you may have already noticed that the conditional probability distribution It's not the interventional distributions, at least in this case. So this is why we need causality for this application. Because without that modeling, maybe we cannot get such method or conclusion. Good. This is one example of why we need causality, or how can we use causal knowledge or causal graph for some applications. Then let's move on to think another question. Okay, so now we know we can use causal graph for some applications. However, how can we get such causal graph beforehand, right? Yeah, well, it is helpful, but where can we get it? In most of the case, we don't have the causal graph. But for example, we could have it from textbook, from domain knowledge. We could construct some graph like that. But what if we don't have that? Then it will be super expensive, time consuming, or we need to do some experiment like the randomized control trials. Well, in many applications, the golden standard is still the randomized control trials to get this causal knowledge, or to create this causal graph. However, we are thinking, can we get causal knowledge or this causal graph purely based on observational data? Does this sound good or possible to do that? Because we have a lot of data. Can we really do the data mining to get the real knowledge from that out of it? Well, we have a very famous quote tells us, okay, correlation is not causation. Well, not really, because it is not. So if you use the statistical method, you may have some problem because misleading is not causation. But it doesn't mean we cannot do that. It doesn't mean we cannot use observational data for the causal discovery. It means that we need to do more things, more rigorous things or methods to get causal relations from the data. So for example, we may need some maybe we need some meaningful assumptions, or probability we need or we may need some principles, which is more general things. And then we could have some causal hypotheses or causal conclusions based on purely based on the observational data. Well, in today's talk, I would like to introduce so here is the causal discovery method. Here are the causal discovery methods, and today I will only introduce some of them. And you can see that there is one class of method which is named by the constraint-based causal discovery method. So this class of method is trying to use the independence relationships in the data to infer a causal graph under some assumptions. And the second category, which is score-based method, it defines a score function to evaluate the causal structure, and that function satisfies some constraints or conditions. And you can design your score function for your applications, and then we could optimize this score function. And the graph structure with the best scores is the ground truth causal graph. So this is the second categories. And one of the commonly used method is GES. I think I gave the reference somewhere later. This is the second categories. Actually, the third categories, so these methods, so they are more recent, maybe recent 15 years. So this is named by functional causal model. For example, LINGAM means linear non-Gaussian acyclic models. The second one is additive noise models. The third one is post-nonlinear models. And I will introduce, and then the last one, so there are many other methods left. For example, the entropy-based methods. I remember there are some works in KDH, which is based on this entropy method, or information theory-based method. And there are also the independent causal mechanism-based method and others, but I will not mention it. So there are a lot of works recently, and I will not have a chance to introduce this method. Well, let's move on. Yeah, so this is basically the outline of today's talk. So firstly, I will introduce the constraint-based method very briefly because I don't have enough time this talk. And then I will introduce some extensions of the method. And this, on the second row, you could see these are more recent works. And I give the link here. And I will share this slide. And you can directly check papers with the link. Yeah, so the first row are the mentioned causal discovery method. And the second row are the methods related to the machine learning methods or models. And the blue and the yellow one, so these are more recent methods. Okay, and then first I will introduce one of the constraint-based methods, which is PC algorithm, named by Peter Clark, and some extensions. For example, in this talk, I will introduce the missing data problem. Of course, there are some other problems like selection bias and so on, but I don't have a chance to introduce it. And for the second category, I may not have time to introduce it. Yeah, I would like to refer the audience to read the paper regarding that if you have interest to this like optimization-based method and the score-based method. And I will introduce these functional causal models in this talk, and one method trying to use normalizing flow for the causal discovery and causal inference. Well, let's start. Well, firstly, before I introduce the constraint-based method, I would like to highlight some very important concepts beforehand, because I was confused about these concepts for a long time. For example, DAGs, named directed acyclic graphs, and causal graphs. Well, what are the relations between these two concepts? Maybe we could first have a look at DAGs, directed acyclic graph. Well, this is a very effective way to represent our human knowledge, like prior knowledge, domain knowledge. We can summarize our knowledge in a graph. Each node is a factor or random variable, and the directions actually, maybe they are indicating the causal directions implicitly, but here actually it encodes the conditional or independencies between variables. And then it tells us, and it gives us the local and global Markov conditions. And I will introduce these later. Now this is actually the DAG, one DAG. And regarding DAG, there are a lot of methods for it, like Bayesian network methods. There are a lot of work in PGM, probabilistic graphical model. We could use that tools for the problems regarding or using these DAGs. Okay, and actually there is a very close relationship between DAG and causal graphs. And recent causal discovery methods, so most of them are actually based on this assumption, acyclic, which is DAG. Then we could have a look at what is causal graph or what is causality. Well, it is a way of causal So causal reasoning is a very important way of human cognition, and we actually reason about so many things with this causal sense. So this kind of subjective thing. And for example, I could give you some example. So like the sun raise up. So we have a sun raise up. Then we observe that a bird will sing a song. But so this is one direction. So the sun is the cause of a bird singing a song. And then actually we don't have another direction back to tell us that, okay, the reason why sun raise up is a bird is singing a song. So that means we don't have this causal relationship. So I will call it the direction. We don't have direction from this observation to this observation. So we only have one direction to go. So this is acyclic. this graph is very simple. There are only two variables here. This is a DAG, I see. And then the second example is that, okay, we have a bird, and then we have egg. Yeah, this is one direction. Another direction is that, okay, we have an egg, and then we have a bird. So this is a very like typical cyclic causal graph. So a causal graph can be a cyclic. So it is not necessary to be acyclic. And there are many cyclic causal graphs. And recently there are a lot of works. I mean, there are many works. Yeah, not a lot. There are many works trying to solve the problem of directed cyclic causal graph. But it is out of the scope of today's talk. So today, let's only think about DAG. Yeah. Then a DAGs can actually be considered as causal graphs. And this is so now I introduce this from the perspective of constraint-based method, causal discovery method. So in which case we can say a DAG is a causal graph. So I use the interpretation from a Dominick's work here. I share the reference here. It's like, okay, a DAG is a causal graph if is acceptable. So this statement is acceptable if or only if the joint distributions satisfies the Markov condition with respect to the DAG. Of course, there is another interpretation of it. So the second one is more related to economics. Well, today's setup is more machine learning way. Yeah. And then how can we understand this statement? So what does it mean, the Markov condition? And actually, there is a local Markov condition. There's another like global Markov condition. And I would like to interpret causal relationships in the sense of local Markov condition. Well, the local Markov condition tells us a very informative information thing. That is, given a variable of interest, we only need to know the parent variable of it, or the parent node in the graph. Then we know that the variable of interest is independent of everything else except the descendants of it. So that means we don't need to look after all the variables. We only need to look at a few variables, which is a subset of the whole variables. They are sufficient for us to know about the variable of interest. So this idea, you could apply it for like causal feature selection, or you could increase the robustness performance of machine learning methods of your models. And it has been applied in many machine learning models, this idea. But actually this idea, so this statement is trying to interpret the causal relationships in a DAG, right? And actually, this is the constraint-based causal discovery method perspective. Okay, now I think we are ready to know something about constraint-based method. And first of all, I would like to introduce two very important assumptions of this constraint-based method, especially PC today. Of course, there is another one, which is minimality. But for understanding the method, I think these two are very important. For example, the first one is causal Markov condition. Actually, it tells us that the causal, so now given the causal relationship in a graph, so we have a graph right here. We have the causal relationships. We know the fever state is a cause of the medicine, which means, yeah, I have already introduced that. Okay. And then given these causal relationships, actually, first step, we have these separation relationships, but I will not introduce that today. So given the causal relationships, we have a way to know, okay, the statistical dependencies in the data, that conditional independencies or independencies. So they are consistent. So given the graph, we can say, okay, what is happening in the data, or what are supposed to be in the data. Moreover, actually for causal discovery, we care about another direction, because we are more interested in that. So given the data, we have all the data, we want to say something about the causal graph. So we have the data, but we don't have the graph. So how can we say something about the causal graph? Then the second assumption is trying to tell us, okay, given the statistical dependencies in the data, So the conditional independencies, so dependencies in the data, it can infer the disseparations or the causal relationships in a graph. So they are supposed to be consistent with each other. Yeah, so this is a quite powerful one. So it's quite strict. So there are a lot of discussion regarding this assumption. But let's have a look at in which case the faithfulness assumption can be violated. Well, let's just recap this causal graph. We care about the medicine variable and the status of patient. Actually, there are two paths between these two variables. The first thing is a direct cause. Second thing is through this confounder. And in the case that one path, the effect along one path have a negative influence, and another one has a positive one. And these two together, they are cancel out. Then the data will not observe any correlation or any hint about the causal relation because they are cancel out. So this is actually a violation of faithfulness, because faithfulness assumption tells us that what you observe in the data can be used to infer the causal relation in the graph. However, if you have something like this happening, you cannot do that. So this is a violation of the assumption. Okay, so now maybe we could have a look at the PC algorithm. So PC algorithm, we could think this as a package in Python maybe, or it is a function. The input is data. So of course, I think I would like to emphasize the assumptions of causal discovery methods are very important. So that assumptions are actually indicating the view how we understand the causal relationships and the results. Okay, so given the function, we input the data. There are two steps to do PC algorithm. And after these two steps, we return a completed partially DAG. That's it. I will let you know later about it. Okay, so this is the ground truth of a causal graph. And we can generate data based on this graph. Okay, now we have the data. So firstly, we initialize a complete graph like this. So everything is connected with each other. The first step is skeleton search. So it's actually checking every pair of variables, whether they are conditionally independent or independent with each other, given all the subsets of the remaining variables. So it will check every pair of variables. But of course, there are efficient way to do this. And once we found that, okay, X is independent of Y conditioning on some variable, we remove the edge. So we don't have the edge here. Similarly, we remove the other edges here. Then we have a result, which is the skeleton. We name it by causal skeleton, which is the end-directed causal graph. So the causal graph, the end-directed version is actually the causal skeleton. And then we come to the second step. We will orient the edges. And we will follow some rules summarized in the algorithm. After applying that rules, we'll have the direction of some edges, but we will not have all. And I will explain that later. And then this is actually the result of PC algorithms. And you can see that we don't have all causal, okay, miscause, but we don't know which one. And so actually we're using the causal sufficiency assumption here as well. That's why we can say, okay, there's one causal relationships here. There's one cause here. Okay, and yeah, let's move on. So now we know what is PC algorithm, and we just have, maybe now we could understand some about the results. So why we can only have part of the causal relationships, not all, because we have, but all of them are in the same Markov equivalent class. So for example, here we have, I'll show you like a 3 variables case. So we have 3 x, y, z, right? These 3, they are equivalent to each other in the sense of deseparations. So they have the same deseparations. So they have the same statistical dependent. They are supposed to have the same statistical dependencies in the data. So that's why we can now distinguish them. However, for this case, they have the same causal skeleton, but they have different deseparations. So we can distinguish this one, which is the collider case, with all the others. So that's why we can orient. The causal direction for this case. And of course, there are some following rules which can be applied based on this. All right. And then there is a theorem, say that 2 graphs, they are Markov equivalent to each other, if only if they have the same skeleton, causal skeleton, and they have the same colliders. Yes. So then that's why we have part of the oriented graph. Now we know our first causal discovery method. Of course, there are many limitations of it, and there are many challenges of it. So for example, the model limitation, like we cannot use it for the dynamical model or the dynamical scenario. And we cannot use it, at least this version PCR, of course, we can extend it too. And for time series data, we cannot use it, at least, you know. And for cyclic graph, for sure, we cannot use it with this version, because of course you can use it, but the results will be misleading. And especially the bivariate case scenario, we cannot distinguish a pair of variable because they are in the same, because like a pair of variable, one calls another one, they are in the same Markov equivalent class, so we cannot distinguish the simplest case, right? And when we apply this PC algorithm in the applications, we have a lot of practical challenges. For example, the missing data problem. What if we have missing data? What if we have selection bias? And what if we have some variables which is unknown there, which is a confounder? And for example, the heterogeneous data. So these are all the challenges for causal discoveries. And this is also the ongoing researches or state-of-art researches focusing on. And I will briefly introduce one of the challenges, which is the missing data I was working on. That, so given the causal graph here, we can generate data. We can generate data. So now I will very quickly mention the else of the talk. Good. So we have a causal graph here. We can generate data of it. And this variable y, actually, there are missing values of the variable. And you can use the code to generate data. And here, these variables are actually missing. And then one way to deal with the missing data is that we just delete all the records, included the missing value. And then we use the deleted data set, the set left, we apply PC algorithm to it. However, actually in our study, we show that the conditional or independence relationships in the data set after deletion can be different with the one with the complete data set. And if you use that one, actually you can have a misleading results. And then we recover the independence relationships with some method using the incomplete data, and then we can recover the wrong results. Yep. Let's move to a more recent studies. Actually, this is the important part of the talk. Yeah. So now let's move to another scenario. So the following studies are more recent ones, maybe recent 15 years. Yeah. So now let's just consider the simplified scenario. We have only 2 variables, and we know one of them is a cause of another one. But how can we distinguish the cause from the effect? Can we use PC algorithm, or can we use statistical independence to do that? Well, maybe we could have a look at some examples here. Like we have 2 variables, so they are both of them are Gaussian distributed. Then yeah, we see x and y and see whether x is the same. And then we see another scenario that, okay, we have uniform distributed x, but we don't know about y, right? And then we see something observational data like this. And then we look from another direction, like, okay, but they look different, but they look the same. So what is happening here? Why when I change the distribution from Gaussian to uniform distribution, it looks different? So here, the hint is here. The idea is here that I generate data using this, like this linear. This is a linear model. We have x and a noise here. You could think this is a linear regression model. E is the residue, x the variable, x is the cause, and then I generate data. And here is actually I'm actually using the uniform distribution x and e, right? And then if you have a closer look at the residue, now we have the data, we apply linear regression on it, and then we have the residue here, ey, and then here we consider another direction to fit the regression model. And we have a residue here. But for Gaussian case, I don't think they have any differences with each other. But for the uniform distribution case, there are some different things. We can observe that the residue is actually not independent of the cause, the hypothesized cause, but here it is. And actually only the ground truth direction, like all x causes y, we have this observation. In another direction, we don't have that. And this idea is very important for the identifiability of causal direction. And let's have another formulation of the same of the observation. Right? So actually, we found that. So we know this is a linear function, linear formulation. We have some noise distribution like Gaussian or uniform distribution. And here we have hypothesis like x causes y, which is using this y equals to ax plus noise to generate it. Then we observe something like that. So under this assumption of data generation process, maybe there are some condition. And under that condition, we can say, if we apply linear regression to the data, we'll have different observations regarding the x and the residue. For example, x is independent of the first residue, but y is not independent of another residue. And this idea is true. I mean, this intuition is actually true. And we can use it to identify the causal relationship of two variables. And how? Actually, we have to introduce the functional causal models, the concept of functional causal models here. So this y equals to fx and the noise, this is actually the functional causal model. And it assumes that the x, which is the cause, is independent of the noise. And then the effect, y, can be represented by the function of the x cause and the independent noise. And then if we further, but on its own, we cannot identify the causal assumption. But under some assumptions, it become identifiable. The causal direction become identifiable at once. For example, the assumption is additive noise model. So this is very common in machine learning. We have additive cause models. And FDA, you may think this is like Gaussian process or a deterministic nonlinear function, and E is like some random noise. And here there's a more general version of it. It's a post-nonlinear model. Of course, there are some assumptions of the function f and the g. And x is the independent of the noise, the independent noise here. And if we just rethink about the whole model, the functional cause model, it's actually trying to model the data generation process with two things. One is f, trying to capture the data generation process, if you think about the additive noise case. And then we have another factor, which is noise. This trying to capture the stochastic behavior in the observational data. And then we have the x and y. And this is quite powerful. Why? Because under some assumption, the causal direction, which is in the same Markov equivalent class, become identifiable. And actually, these functional causal models, so it has a close relation with the many machine learning methods. Well, there are 15 minutes left. I will have a very quick introduction of the last part of this talk. I don't think I have enough time for the score-based method, but I will go through the last example, which is the connection between functional causal model and normalizing flow. Like functional causal model, in this case, you could also call it like structural causal model. Then we have this causal graph. We can write down the corresponding functional causal models or structural causal models. And if you are familiar with the Bayesian network, you can factorize it in this way. And let's just call it causal order or causal factorization. Let's just keep this in mind. We have a causal order to factorize variables, and we have a corresponding structural causal models. You can see they are corresponding to each other. And there is a very important concept named by independent causal mechanism, which you can directly get it from this formulation. Okay, and then we have this normalizing flow. Well, I don't think I have enough time to clearly introduce all the details of normalizing flow, but I will quickly go through it. Like the normalizing flow, you can use it to do the density estimation. So actually, it hypothesizes some simple distribution which are easier to sample from. Then so the normalized flow try to use that distribution to estimate a more complicated distribution here, like ZK. And it do it in a compositional way, like neural network, one layer, another layer, until the final layer. And it's actually using the change of variable formula, X. So we may think X, it is observational data or variables, Z, Gaussian distribution, the hypothesized variables. And we can estimate the observational data distribution with a simple distribution, Gaussian distribution, and a Jacobian function of this function f in a compositional way. And this f is actually a neural network. And a concrete way is we can write it down. We can write down the f in this way, which is an autoregressive model way. And what is autoregressive model? Is like, okay, you could have it, but let's assume you know what is autoregressive model. You can write it down in this way, and then you can write down the Jacobian of Z in this way, the determinant of the Jacobian matrix in this way, and you can easily compute the Jacobian matrix. And you can, let's assume we can learn the function f with data. Now I will highlight what are the relations between autoregressive model and causal factorization. Right? So here is the causal factorization. If we go back to the autoregressive model, it is actually can be used to factorize the joint distribution in a specific order. So we can factorize it in this way and this way. They are equivalent with each other. And actually, the causal factorization is one of the autoregressive factorization. And all of them, so let's assume, we just use normalizing flow. So autoregressive normalized flow, we have this nonlinear functional form. We just need to learn this normalizing functional form from the data, then we get the model we want to have. And so now since causal factorization is one of the autoregressive factorization, so I'm representing the work which is highlighted here, then can we use autoregressive normalizing flow for causal discovery or causal inference? Well, actually, yes, we can do that. So now we can we write down the causal structural causal model, x1 and x3, and the function are actually the neural network. So it's a vector. We have vector z, we have vector x, and we have a function. And this is a normalizing flow, autoregressive normalizing flow, and the f can be written down in this way, and we can learn it with this maximum likelihood function, maximum likelihood. Yep. And actually, we can use it for causal discovery of causal inference. Suppose we have the causal graph. We just need to learn the parameter of the functions here, and then we directly apply it as a normal causal inference method. So given the structural causal model, we definitely can do causal inference. So there's no doubt about it. Then the question is that, can we use autoregressive normalizing flow model for causal discovery? Well, we could think in a simple scenario that we have two variables, and which now the causal discovery task is just to distinguish the causal direction. Suppose there's a relationship between each other. Then which one is the causal one? Again, we go back to the bivariate case. And now we have two causal hypotheses. So we can factorize this joint distribution in this way, in the first way, A way. We also factorize it in a second way, which is the B way. And then we can write down the corresponding structural causal model, which is corresponding to two different autoregressive normalizing flow. And then this work actually tells us that we can use, so the one with causal direction, that one has larger likelihood. So you can do the model selection with likelihood ratio, which is proposed by this work. And then you just use it for causal discovery. You compare two models, then you get choose the better one, which is the causal one. Yeah, and there are definitely some limitations. Could be solved later in the future work. For example, here, how can you make it? So for example, how can we apply this idea to a larger graph? For example, we have like 10 to 20 nodes. Then we have to enumerate all the causal graph, then compare each other. Then we may need to learn a lot of autoregressive normalizing flow, which is problematic. Yeah, so the model selection procedure could be the future work, definitely. And that's it. And then we can conclude that, okay, we can use autoregressive normalizing flow for causal discovery.